This is Matt Modena from ASM International, and as the world's trusted, agnostic, and nonprofit source of materials information and data, we are happy to be bringing new simulation tools to the market. ASM Data Ecosystem lowers barriers to entry by delivering advanced analytics, faster innovation, and increased digital accessibility to the engineering and manufacturing communities. This quick use case featuring DANTE Solutions will discuss how to adjust your recipe to meet core hardness specifications.
You've been successfully making a part out of AISI 8620 for a long time. You know your steel distributor uses a number of different mills, but your part has been supplied by only one of those mills. Hitting the minimum core hardness spec of 35 Rockwell C has been a snap. You're usually over 40. The bad news is lately you've been struggling to hit the minimum core hardness and you don't know why. First things first, you want to know that your process is in control. You've checked your quench and still hitting the 30 degree per second cooling rate that works well with this part. That's good news. You now wonder if it's the steel. Looking at the mill certs didn't show anything obvious. The chemistry reported is in spec, but at 18 carbon is a little lower than normal. You wonder if being at the lower end of the carbon range could be a factor. You've had 18 carbon once in a while, but never went below the 35 core hardness requirement. You then realize that this cert is from a different steel mill. You decide to use DANTE Utilities MatSim to figure out what's happened. First, you want to know if MatSim represents your real-world situation. You select the 8620 composition, set the carbon to 0.20, and set the initial amount of ferrite and perlite to 0 since you're simulating the austenitize and quench. For process settings, you select the rate, target temp, and step time option and enter the start temperature of 900 degrees C and a final temperature of 20 degrees C. You also enter the cooling rate of 30 degrees C per second and 300 seconds to make sure that MatSim gets to room temperature. Then click on the red Analyze button. When it turns green, you click on Plot and then click on Settings to show all of the phases. The microstructure is about 60% martensite and the hardness is about 42 Rockwell C. This is good news. MatSim reflects your reality when things were normal. You then wonder, on the new cert you saw a low side carbon of 18. You're wondering if 16 carbon is low enough to drop the core hardness out of spec. MatSim with 16 carbon predicts that the hardness would drop below 33, matching up with your worst case situation. You want to know what carbon hits the bottom of the spec, so you rerun it at 17 carbon and you're right at the bottom. You're now closing in on the problem. You know that even on the same piece of steel, no two labs get the exact same analysis. You also know that certs represent the melt batch and there's permitted variation in product chems known as check tolerances. You send a piece to a local chem lab and you find that the recent batch was at 16 carbon, 2 points lower than on their cert, but still well within the check tolerances. Remember that when you ran the 16 carbon simulation, you got hardness predictions right where your problem parts were. Now you really know what's going on. This was a carbon problem. Your quench was in good shape, but a steel supplier switch by the service center unintentionally created a too low but in check tolerance carbon level, and that was enough to create the problem. You go back to the service center and make sure that you get steel that is always at 17 carbon or above. The new mill adjusts their aims and you now get material that restores your ability to consistently meet the spec.
Thanks for watching this quick ASM Data Ecosystem product highlight. Please reach out for more information or to gain access.